So, let us recall what we did last time, that ideals of S inverse A, this is precisely S inverse I an ideal of A such that S intersection I is empty. Then we defined and we saw that for every prime ideal, or so let me set this notation. If you have already done the some exercises from Mathieu MacDonald, you would have seen this. If A is a ring, then I set this notation spec of A. This is set of all prime ideal. This is called a spectrum of A, or in short spec A. So, this is notation. Then what we showed yesterday was that spec of S inverse A, this is S inverse P, where P is in spec A with P intersection S empty. Okay. So, not only this is even more strong. Suppose I take so I take these two sets, spec of S inverse A. If I send a map from P, so I send this P, so I collect this set of all P in spec A such that P intersection S is empty. Okay. From here I send a map to spec of S inverse A, that P is mapped to S inverse P. Okay. Then this map is, and from spec of S inverse A to set of all P in spec A such that P intersection S is empty. I send P to, so let us look at this natural map from A to S inverse A. Okay. I send P to F inverse of P. Okay. These two maps are inverses of each other. So, if I call this let us say psi 1 and psi 2, then that is psi 1 in composite psi 2, this is identity on this set spec S inverse A, and psi 2 composite psi 1, this is identity on the other set. Let me call this some C. So, here see yesterday we saw I start with an ideal P in S inverse prime ideal S inverse A, then pull it back to A, what you get is a prime ideal. Moreover, if you take S inverse of that ideal, then you get back this P. That is, I did not prove it, but I verify that it is. So, that is basically what I am stating here. So, therefore, this is the map from here to here, or this psi 1 or psi 2, both of them are inverses of each other, that is it is a bijective correspondence. So, here what we are saying is that this is the collection of ideals of S inverse A, all are extended ideals with respect to this map, right. When you have a map f from A to B and I is an ideal in A, then f of I need not be an ideal in B, but then you look at the ideal generated by this set. Okay. This is called extended ideal, i.e. ideal of extended ideal corresponding to the ideal I with respect to this map. Okay. What we are saying here is that every ideal of S inverse A is an extended ideal. You start with an ideal of A containing which is contained in the complement of S, and then look at its extension S inverse A, that is precisely, these are precisely the ideals of S inverse of A. Okay. Now, if so this is, and if you look at this set P in spec A, P intersection S is empty. What we are seeing here is that this P by the proof, or this is the inverse of psi 1, you can see that this P is nothing but contraction of some prime ideal in S inverse A. Okay. So, in this case every ideal is every prime ideal that does not intersect S is a contracted ideal. This is we have a more general statement. So, let me just state it. Let f from A to B be a ring homomorphism an ideal, a prime ideal, and P be a prime ideal of spec of A. Okay. Then P is a contracted ideal if and only if P extended contracted is P itself. I take P, extend it to B, and then contract to B to A, it is P itself. That is exactly what we are having here in this case. In the special case A going to S inverse A, I have natural map, every prime ideal, in fact for us this is true for every prime ideal. Okay. Every prime ideal that does not intersect S in the case of S inverse. Okay. So, this is straightforward. If this is true, then by definition, see this is P is the contraction of P extended. So, therefore, if P if this is true, then P is contracted. Now, if P is contracted ideal, that means P is equal to some Q contracted for some Q in B. Okay. Now, F inverse of Q is, oh, we do not need to see that. See, P is this would imply that P extended contracted is Q contracted extended contracted, but this is same as Q E C E C E C, any ideal contracted extended and then contracted is contracted. So, this is Q contracted, this is P. So, this is kind of straightforward. So, here when is in the natural case of A to S inverse A, when is an ideal contracted? It is when the prime ideal does not intersect the multiplicative set S. Okay. And when it does not intersect the multiplicative set, we have this is naturally true. More properties of S inverse A. So, if I have I1 up to In is a finite set of ideals, the set of ideals, then S inverse of summation I j, this is same as summation S inverse I j, j from 1 to n, S inverse of intersection I j is same as intersection S inverse I j. Okay. This we proved for 2, but it is one can extend it to the case of many. Another important observation is S inverse of radical of I is same as radical of S inverse of I. So, let us take an element here, okay, x by s in S inverse of radical of I, x in radical of I. This implies that some x power n with x in radical of I, and that implies that x power n is in I. That means x power n by 1 is in S inverse I, and that implies x by 1 is in radical of S inverse I, and that clearly implies that x by s is in S inverse of I mean radical of S inverse of x power n is in I, this is in I, this I can write it as x by 1 whole power n. Conversely, if x by s is here, that means x power n by s power n is in S inverse I, right. That means I want to say that x power n belongs to, so x by s is in radical of S inverse of I. That means I can write x power n by s power n is in S inverse of I. Every element of S inverse of I looks like some element in I divided by this. So, this I can write that x power n is in I. This implies that x is in radical of I, that implies that x by s is in S inverse of radical of I. So, this implies S inverse of radical of I is equal to radical of S inverse of I. Another nice property of localization. So, I mean this localization is such a process that we are seeing now, that it commutes with, I mean commutes, distributes with all operations, whatever we can think of, summation, intersection, taking radical, and if I and j are ideals of A with j finitely generated, then S inverse of I colon j is same as S inverse I colon S inverse j. So, this is again I will this I will leave it as an exercise, because if I take what is I intersection an ideal generated by x1 up to xn, this is same as intersection of I from 1 to n. Okay. If j is finitely generated, let us write this j like this, then I colon j is same as intersection of this form. This is exercise, this straightforward. See, for j to be multiplied inside I, every element each xi, it is equivalent to saying that some A multiplies j inside I is equivalent to saying that A multiplies all of them x1 up to xn inside I. That is exactly on the right hand side. These two are equivalent statements, therefore, these two are equal. Now, you only have to prove using the intersection property, I only have to prove S inverse of this to say that S inverse of j, I only have to prove it goes inside. That is how did we prove that nil? So, nil radical of A is intersection of all prime ideals. How did we prove that? We proved this by saying that if I take any nilpotent element, it is there in every prime ideal. Okay. Conversely, if I take an element which is not nilpotent, there exists a prime ideal that avoids this. Okay. So, the second part can be viewed using the localization technique. See, if I take the correspondence between prime ideals of A and S in, I mean it is not really the correspondence. I take S to be equal to f power n. So, let me write x be a non nilpotent element, then 0 is not here. Okay. And that implies that S inverse A is non-zero, it is a non-zero ring. Therefore, there exists a maximal ideal M in S inverse A. If I take P to be F inverse of M, F is the natural map from A to S inverse A. Then this has to be a prime ideal, right. This is precisely the 1-1 correspondence that we talked about in the beginning of the class today. So, this is a prime ideal. Can it contain F? This, see, F M is a maximal ideal, proper ideal. Okay. So, inverse image, because of the 1-1 correspondence, the inverse image is again a proper ideal. Therefore, this cannot be entire ring, which means F cannot be here. See, F is not here, it cannot be here. I mean M, what are the prime ideals of, I mean maximal ideal is a prime ideal. Okay, what are the maximal or prime ideals of S inverse A? All S inverse P where P does not intersect S. So, here S is this. So, X cannot be X cannot be in P. this implies x cannot be in P. So, this is one direct application of that 1-1 correspondence, but nice way to view the this property, that if x is not a nilpotent element, then there exists a prime ideal that avoids this element. Yeah. So, now if that is again property of nil radical of S inverse of A is equal to S inverse of nil radical of A, follows directly from the definition of the follows directly from the property of bijection between prime ideals of A that not intersecting S and prime ideals of S inverse A. Okay. So, this is property 5, I will call. Nil radical of S inverse A is S inverse of nil radical of A. Now, let us move on to the module setup, prove some of them over the modules. So, let M be a finitely generated A module, then S inverse of annihilator of M is equal to annihilator of S inverse of M. So, localization commutes with even annihilator. Yeah, we will see. Okay, so the first something that one should think about, we talked about these S inverse of summation I n I j j from 1 to n. This is same as j from 1 to n of S inverse I j, and two properties that S inverse of intersection I j j from 1 to n. This is same as j from 1 to n S inverse of I j. Okay. Sorry, I am sorry. This is intersection. Okay. Where does it fail if you take it to infinite sets? Okay. Can you think of some example where this is not true if I take infinite sets? So, you can think of a ring, a collection where this is very very small, but each of them is big. Okay. If if you are still it's not sparking, then you can think of where the intersection is 0 while each localization is whole ring, whole of S inverse A. Okay. Think of this. Okay. And again similarly this one, there you have to think the converse, like whether this can we construct sum of ideals where this is think about this. But in this one it's, I thought it was fairly straightforward to think of. In Z you take A equal to Z. So, what is ij, ideal generated by j, maybe in is ideal generated by n. What would this be? I mean j from n from 1 to infinity, that will be 0, right. There cannot be any integer in that. So, this will be 0, and what is s? All z star you can, or n natural numbers, then this will be 0, but each S inverse j will be whole of q. S inverse j will be q for each j, therefore that will be, this will be 0 while this is. So, similarly try to construct for this, okay, think of that. So, what I am trying to say is that the properties that the commute S inverse commutes with, they are we are assuming they are finite intersection, finite summation and so on, okay, without which it need not necessarily be. Okay. Let us look at the proof will now reveal what happens. So, first of all, if I have okay, suppose M is generated by a single element, okay, suppose M is generated by a single element, then this annihilator of M is same as annihilator of this module, the element M. Anything that completely annihilates capital M should annihilate this one. Similarly, if an element annihilates M, it annihilates the whole of M, because every element is a scalar multiple of this. Now, therefore, I can have a map from A to M, A going to A M. This is a surjective module homomorphism, and what would be the kernel? Kernel phi is annihilator of M, small m or capital M, whichever one you want to write, one can. So, M is isomorphic to A mod annihilator of M in this case, right. That would imply that S inverse M is isomorphic to S inverse A mod annihilator of M, okay. But this is isomorphic to S inverse A mod S inverse annihilator of M, now S inverse M is generated by again this M, and a map from S inverse A to S inverse M will be A M by A by 1 going to A M by 1, that will give me a homomorphism with kernel as this one. Therefore, S inverse of, and this is same as S inverse A S inverse M. So, this directly says that S inverse of annihilator of M. See, here there is one more catch, that can you see that one of them is contained in the other? S inverse of annihilator of M and annihilator of S inverse of M. If I take x in the annihilator of M, that would imply x by 1. So, x x m is 0, that would imply x by 1 times m by 1 is 0. That would imply that x by 1 is an annihilator of S inverse of m. Okay. So, if I take x by s in S inverse of annihilator of m, this would imply this x by s is here. So, this is contained here, and we have this isomorphism says that these two have to be equal, otherwise this modulo this will be non-zero. So, okay, so we proved this for m equal to m to be a cyclic module. Now, we make an observation. If n and p are submodules of m, then what can you say about annihilator of n plus p? This is annihilator of n intersection annihilator of p. Right? If I take any element here, it annihilates elements of n as well as elements of p, therefore, it has to annihilate elements of n plus p. Conversely, every element of n is contained in n is contained in n plus p, therefore, annihilator of n plus p is contained in annihilator of n. Similarly, it is contained in annihilator of p, therefore, this is contained here. So, this equality is a straightforward verification. So, if I have S inverse of annihilator of n plus p, this is S inverse of annihilator of n intersection annihilator of p, but S inverse goes inside finite intersection. So, therefore, this is equal to S inverse of annihilator of n intersection S inverse of annihilator of p. Okay. Now, if n and p were cyclic modules, so n, this is equal to annihilator of S inverse n intersection annihilator of S inverse p if n and p were cyclic modules. But annihilator of some module intersection annihilator of another module is same as annihilator of S inverse n plus S inverse p. The same equality I am using here. That is what we proved, only we proved for cyclic modules. We have proved only for cyclic modules that S inverse of m, annihilator of S inverse m is same as S inverse of annihilator. So, from here to here we need n and p to be cyclic module. Now, take m to be a finitely generated module. Take a finite generating set x1, x2 up to xn and write m1 mi to be the submodule generated by xi. So, therefore, I can write m as m1 plus m2 plus etcetera mn, apply this there. So, now here we need S inverse distributes inside, for that we need finite intersection, without which S inverse do not go inside. Okay. So, that is where we are using that it is a finitely generated module. Again, if n and so this is 7, if n and p are a submodules of M and P is finitely generated, then S inverse n colon P is same as S inverse n colon . So, here also the proof is well. So, in this case let me make another observation which I do not remember whether I stated this. N colon P is same as annihilator of n plus p mod n, or p plus n mod n. See here, if I look at m mod n, okay, I look at m mod n and I am looking at the submodule generated by p, that is precisely this n plus p mod n, submodule generated by p. Its annihilator, we are looking at the annihilator of p, or in other words I am looking at all elements which will kill p, or in other words all elements x such that x p becomes 0. Here what is meant by 0 here? It is contained, it goes inside n, or in other words all x such that x p is contained in n, that is basically precisely the annihilator, that is the meaning of this as well. Okay. See, annihilator of, so you take any module k contain this, okay, this as a submodule of m mod n, this is precisely set of all x in A such that x k by n is x dot k by n is 0 plus n. This is same as saying set of all x in A such that x k is contained in n. Right, and that is precisely n colon k. Now, in our case k is n plus p. This is, so if I take an element that multiplies n plus p inside n, which is same as saying that multiplies p inside n, because the other one is anyway there. So, therefore, this is equal to this. Now, we can use the previous property that we proved. S inverse of n colon p is same as S inverse of annihilator of n plus p mod p, but this is annihilator of S inverse of n plus p mod p, sorry, n. So, here we are using the fact that p is finitely generated. P is finitely generated, therefore, this is a finitely generated submodule of m mod n. Okay. Therefore, this is equal to this by the previous property, but this is same as, now I can take this further, this is same as S inverse n plus S inverse p modulo S inverse n, but now I use this property once again to say that this is same as S inverse n colon S inverse p. So, these are the some of the most important properties of localization that we will be using. Now, we will further many times we will be using what is called localization with respect to a prime ideal. Okay. That is where, as we saw in the last class, that many properties, if you want to prove a module is 0, you only have to prove that localized at every maximal ideal is 0, or some map is injective, you can localize and say that for every localization, this is for every localization at any maximal ideal it is injective. This is of use when your ring is local. See, if your ring is local, there is only one maximal ideal. So, if you just localize at that and say these are these are the properties, we are through. Okay. Flatness, injectivity, surjectivity being 0, there are many properties that we have already discussed. So, and most of the time we will be using localization with respect to a prime ideal or maximal ideal. We will see that in the forthcoming classes.